So, so to give you a bit of background to this, this is something you're going to hear a lot. You probably have heard. It's just a directed acyclic graph. And this was something that was brought up at Git Merge in Paris earlier this year. Emma Jane Hodgman-Westby is an educator. She teaches people about how to use Git. Not people who are nerds, people just trying to get through the day and get the job done. And telling them it's an acyclic graph is bugger all use for anything. What you really need to do is say, okay, this is how you get your job done. It's task-oriented. Let them sort of work through themselves. Okay, I want to do this. Let's try and use Git to get the job done. But the reality of the situation is that this is not always going to get you through the hard times. The reality is that Git is an acyclic graph, or it's a set of objects. I'm not going to use acyclic graph again because it's never made any bloody sense to me. It's bugger all use for teaching Git. But when you hit these tricky times, where you've got multiple merges going on, you've got rebases, you've got forced pushes, all these things happening, understanding what's happening underneath the hood is very, very important. Without this internal mental model of how Git works, it's going to become confusing because Git's abstractions are very leaky. You tend to discover how it works whether you like it or not. It's one of those things like driving a car. You don't have to know how an engine works to drive a car, but if you know how an engine works, you'll be a better driver, or at least be a little bit easier on the car. So this is one of those cases where a little bit of knowledge can go a long way. So to follow up on that, well, let's just jump straight in. We're going to take you through the basics of Git from the absolute bottom layer and all the way up to some of the higher level concepts. Git is quite well layered in that sense. There's concepts built on concepts built on concepts. But if you go right to the bottom, it's very, very simple indeed. So at its core, the basic building block of Git is the blob. Now, blobs can be different types of things, but that's ultimately what it is. If you're dealing with Git, you're ultimately shuffling blobs around and linking them up together. And what do I mean by blobs? Well, it's this. What you're looking at now is the entirety of the low-level Git data model. This is it. It's that simple, of course, being extremely deceptive. So what you have here is three types of blobs. One is content. That's just raw data. That is a file you've committed, an image you've committed. Just raw data files. And they are hashed. What Git does, it takes them, it compresses them using zlib, puts a header on them, hashes the result, and then from that point on, that piece of content of the file will always have the same hash. Now, this applies to any changes as well. If you change a file and you add it to Git, it's a different hash. Therefore, it is a different object. And this is how it tracks it over time. Every change is different. And this is what they mean by content addressable file system when you hear that phrase. Every piece of change, every change is a unique hash in there. But objects by themselves are not of use. You need to kind of tie them together. The next level up is the tree. The tree is also a blob. It goes through the same process. It's hashed, it's zlibbed, it's compressed, it's hashed, and then it's dropped in a directory. A tree is very much like the Unix level file system, really any file system. It's just a file that lists a bunch of files by their hashes, their file names, some metadata like the file mode, whether it's executable, readable, writable, etc. And it may also point to other trees. So directories can contain other directories. Trees can contain links to other trees. They may also link to other trees and eventually to a file. At the higher level than that is the commit. This is what you're used to dealing with in Git. You don't have to. You can actually operate at a much lower level than that if you're prepared to go through that process. But the commit is the general unit you're working at. It's how we think about the history. Commits point to trees, they point to files. and commits can point to other commits. They can have parents, and importantly, they can have more than one parent. But this is all theory. Let's have a look at the actual practice. This is like how you can muck around by yourself on your computer. So, can everyone see this? No. Can we possibly turn off these the floodlights? Yeah, so here we go. So Git init creates, as you probably know, creates a new Git repository. And inside that is, all it is a .git directory. And inside there is all the metadata that Git contains. And it's complete, as you probably know. So let's look inside the Git objects here. There's nothing in there. It's a new repository. It's empty, so there's nothing to track. Let's add something. Touch is just a Unix command that will either update the modified time or create a file. So we're just creating a purely empty file here, and we do git add. As you probably know, that doesn't actually create a commit. It doesn't give it history. It just says, I want you to be aware of this file from now on. This is something I want you to track. And I'll tell you when it's changed. So let's go back and look at that again. The tree command, by the way, is outputs a pretty printed version of the directory structure. So as you can see here, it creates a blob. This is it. This is your basic unit. That empty file has been added. It's been compressed, which in an empty file makes it actually larger, and then adds a header onto it, and then puts it in a directory. You may notice it's also that E6 at the start. What it does is it spread the load. You're going to be creating tens of thousands of these over the course of a project. To spread them out, rather than dumping in one directory, it uses the initial 2 digits to kind of spread them out across different subdirectories and stop overloading the inodes. This is one example. This is written by Linus Torvalds in the original prototype, and he's a file system operating systems guy, so he's thinking about how to spread the load. But this is it. You've added that file, and now there's an object in the tree. So that's pretty much it. Now, obviously, just dumping objects in there with no real way of tying them together is pretty much useless. So we're just going to create a commit. Very simple. And this is it. That's the blob, the original one we looked at. This is the tree. This has a single entry in that tree that points to that blob, and we have the commit, which points to the tree. So that is pretty much the anatomy of a commit. Now, interesting thing I should probably mention here, this blob, which contains an empty file, has a hash. That hash, any empty file in any repository anywhere in the world is always going to have that same hash. That's what we're talking about by a content addressable file system. What the file contains defines what its identity is. So this is what we already got, but this is not used by itself either. We want to change. It's a version control system. We want to add new versions to our project over time. So this is what we do. Each commit can point to a previous commit. It has a parent commit. It can actually have more than one parent, a concept we'll come back to in a bit, but this is how you chain them together. Each commit points to optionally one or more previous commits, and that is how you define time. You start off at the end of your project, and you can walk backwards right to the beginning, possibly going via branches, different side tracks, but ultimately that is Git at its core right there. Very, very simple ideas. What this actually means for you and how you can use this we'll come to in a little bit. We'll just show you a few more little key points. One here is let's create an actual commit for our dummy repository. So we create it, we add it, and we notice we have an entirely new blob. This is what I'm talking about. Every addition of a change to a file creates a new blob. Every file change, you take an image, you put it into Git, you change 1 pixel, and it is now a completely new file. Now that can be quite wasteful. Git does use some tricks under the hood to remove that or optimize this a bit more, but you don't need to worry about it too much. Git has this idea that we're not going to try and delta encode everything up front. We're going to always try and store the true state of things, because delta encoding can improve over time, but your files should always remain the same. So that is the lowest level of Git. But once again, all we've talked about so far is hashes. Everything is a hash. Now, that's not a lot of use in day-to-day use. You want to talk about master. You want to talk about my feature branch. You want to talk about this particular version of a release. How Git does that is a slightly higher level concept called refs. And on top of this, it builds branches and tags, which you're probably vaguely familiar with. Tags not used quite as much. Branches quite a lot. Refs are generally not used themselves. They're a low-level concept. So what is a ref? A ref is just a pointer to an object. That's it. It is a way of saying attaching a name to an object, to a hash, the entirety of it. Very much like a variable in, say, the JVM. There is it has an address in memory. You don't need to worry about that address in memory because you've given it a name and you use that name from that point on. So what is a branch? Well, a branch is just a ref pointing to a divergence from the main tree. So a object has a commit has a parent, but they don't all necessarily have the same parent. So I can say, well, at this point, this commit, I'm going to go off on my own branch of control. And we just give that object the parent of that point we want to diverge from, and then we can just add a ref, which we'll call a branch from now on, and that will be we'll use that to track our branch. That's pretty much it. This is why branching and tagging and all these things are very, very fast in Git, because they are nothing more than moving around a couple of little pointers in files. We'll actually show you what it actually looks like in a bit. And what is a tag? You can probably use tags. They're most commonly used for releases, to say this point is, if you want to go back and find this version of release, check out this tag, and you'll get back to that point in time. And again, it's really very simple. The only real difference between a branch and a tag is the tags, by convention, don't change. Branches do. As refs, they move forward in time. Tags remain static over time. You can sign tags if you want it to be super accurate or super secure. But generally speaking, we just trust people to not muck around with tags. There's no reason why you couldn't go into a Git repository and overwrite a tag, but you're just not going to make any friends doing that. So let's have a look at this, again, in practical terms. We're going to have a look inside our Git repository, our simple Git repository here. So the first command I'm doing up here is I'm going to create a tag called a tag. And we're going to give it a name. We're going to give it a message to go with it, which is a normal way of doing things. That's slightly different. I'm skipping over something here a little bit. But at its heart, it's still basically the same idea. It's just a pointer in time. What a tag does with a message will actually create a mini commit object, but you don't have to add a message, so you can create a bare tag that is literally just a pointer to an object. A branch is definitely just a pointer to an object. And if we do this little useful tree command on the git refs subtree, you can see we've created a bunch of files. We've created a file called a branch, and we've created a file under tags called a tag. And if I cat that file, cat just blasts it out, just dumps it out onto the screen, what the contents of that file is. That is it. That is the entirety of what a ref is just a pointer to a hash. This, again, is why branching is so fast under Git. It is literally writing, I think it's 128 letters to a, no, it's less than that. Whatever number of letters that is, it's writing it to a file. So it happens pretty much instantaneously. So that's basically the next level up. I'm going to talk about how we manipulate this on a day-to-day basis. How many people here have used reset in Git? Yeah. How many people screwed it up and blew away a chunk of their report? Yeah, it's basically a rite of passage. I'm going to show you how to get out of that situation. Reset hard, it's great, it's awesome. This is what reset is. Reset moves refs around. Now you can literally do this if you wanted to, by just going into that git refs directory and overwriting that file. Just going and having to dig around, finding what an alternative hash is and just shove it in there. So that's all reset is doing. Now I am glossing over something there. Reset has different modes, and it will also modify something like your staging area and your working tree. And hard is particularly aggressive. It will blow away any changes that you have uncommitted, things like that. But at its core, again, it will just shift the ref. Now, so at this point, as you can see, it doesn't actually destroy any data that's actually inside your repository. It just hides it. You have to know the magic hash to get back there. So I've reset it, I've screwed up. How do I get back to that state? Well, I don't know. I have no idea what the previous hash was, and I'd have to go digging around the repository with possibly tens of thousands of objects in it to find out which one was my magic object from the past. Or we could use RefLog. Every time you modify via Git, not via directly manipulating files or anything, but every time you do a reset or other manipulation of references, Git keeps a record of it in a history file that's called the RefLog. So if you screw up anything, you do a rebase, you do a reset, and you decide, I want to get back to that previous state, that state I want an undo. This is it. If I can look through here, it's mildly commented. You've got to kind of know how to read it a little bit, but it's fairly obvious if you know the history of your project itself. But what we do is we can look up what the previous hash was. So we're back to hashes again. So we look up, we go, here's where we moved ahead. We want to actually go back to the previous version. I shouldn't have done that. Hang on. Sorry, yeah, we'll come back to that. Sorry, how we fixed that. I thought I was doing something else there. So RefLog is something that keeps a history, but only keeps for 90 days, by the way. Now, as you've seen, when you add things to a Git repository, it creates objects. And if you're doing add, and multiple versions of adding a file to a repository, you're creating a whole bunch of objects which are never actually used. And this builds up over time. So how does Git manage these kind of orphaned, useless, intermediate objects? Really kind of spoil the reveal here. So what it does, it has something called GC. Git, if you think about it, if you ever worked with a JVM or really any kind of object-oriented language, or really any virtual machine system at all, it has the idea of garbage collection. Garbage collection is just find all the objects which no longer have valid references to them and just reclaim them, or in this case, delete them from the disk. So what happens with GC is it runs around finding anything that no longer has valid references to it and will just delete them. It will find all references, walk back through them, find out which ones are dangling at the end of it, and delete them. Now, it's not too aggressive about that. In particular, it doesn't delete anything until it's at least 2 weeks old. However, you can override that. You can set it longer, you can set it shorter, or in this case, use prune equals all will blow away anything. So this is really why, if you do that reset, don't go running around doing GCs, aggressive GCs afterwards, because you're destroying some of your history, or you're destroying your ability to recover. That said, you wouldn't normally do this. Git will generally do this for you. The other thing that it does, and we're down into, I was always reticent to even talk about this because it's not really important, but it's kind of useful to know, or at least interesting to know, is it doesn't just prune objects out the tree, it recompresses them. So what it does is, Subversion originally, or in fact it always stored the differences between files over time. That seemed great at the time, but it meant that if you wanted to go back and actually modify anything in it, it was virtually impossible because you had to basically recreate the entire repository. Git didn't do that. Git keeps every object, all the intermediates, so actually modifying the history is very simple, but it's also very wasteful. So what Git has is something called pack files. When you do a GC, it will temporarily encode all of these spread out objects, find out their history, work it out, and store it in what's essentially is a temporary arrangement of a pack file that is delta encoded and compressed and so on. This is primarily to save disk space, but more importantly, it's very useful for networking. When you do over the network transfers, you don't want to transfer massive objects. You want to only transfer the bare minimum. Just to give you a quick look at this, this is what it looks like. After we do a GC, all these objects no longer exist. They've all been packed down into 3 files. One that references the packs themselves, one that is the actual data, and an index file. This, if you ever mucked around with on-disk databases, it looks an awful lot like this. You generally have an index file and the raw data. So the index file is looked up and used to find the data inside the big blob file. It looks at Berkeley DB or anything like that. It looks a lot like this. If you're really interested in this kind of thing, go have a look. Inside the Git source, there's a file in the documentation that explains how the pack file works. It is deep black magic. It is optimized for spinning disks to hit the disks in the most optimal way possible. Again, this was written by a guy who does operating systems and file systems. It is deep black magic. No one really knew how it worked for a long time until somebody pinged him on the mailing list and said, how the hell does this work? And he just dumped a bunch of information and then he just copied it into a file, and that's the documentation under the Git documentation tree. Interesting stuff if you're really into your hyper-optimized database sort of things. This is basically a mini database. But that's that level. We've talked about the low-level blobs. We've talked the higher-level refs, branches, and manipulating them and how to screw yourself up by manipulating them. We're going to a higher level now. Branching is easy, but branches are not a lot of use unless you can get them onto something else. Unless you're completely replacing your entire repository, you can do that. But you generally want to merge back into the mainstream of development at some point. So what is a merge? A merge, of course, is just we rejoining the history. We've gone off, done our own thing. We've decided it's time to get back onto the mainstream, and there's a merge occurs. It's a bit more complex because some of these changes that have happened between the 2 branches might have overlapped. Often they don't, but it's possible. So let's have a look at a merge. This merge commit that's created when we re-merge these 2 streams of development. What does it look like? Again, very, very simple. It is just a commit with 2 parents. This is why you can go around deleting branches inside Git, and you'll still have the history because you can always walk off. As you walk back through the tree, you can often go down that alternative path, look at what happened, and then come back, or you can just follow down the main branch. You can sort of see it as a sort of winding path that you can go look back on. Of course, getting there is not quite as simple as that, as simple as just saying that, although sometimes it is. This is a fast-forward merge. If your 2 branches haven't really diverged, if you've gone, master, 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 I'm going to create a branch, oh yeah, I'm finished now, done, and no one's committed onto master again, why bother even making a merge commit? All you've done is just, there's nothing to merge. There's no changes. And Git by default will do this. It will do a fast-forward merge. The problem there is your merge commit here doesn't have the 2 parents. So you're losing history. You no longer have the awareness that the branch ever occurred. Maybe that doesn't care. Maybe, possibly you don't care. Some people like a nice, neat tree. Personally, I like to keep context. If you know they branched this off and maybe that branch had a ticket name associated with it, an ID for a Jira ticket or whatever, and then you merge, you may be losing that information. Personally, I like to keep that around. So there is a merge command or an option called no FF, no fast forward, and it will always create a merge commit even though it doesn't really need to. And that's where it just adds a dummy commit that contains the 2 parents so that you know that the branch occurred. But generally speaking, this is not going to happen. If you're in a busy team that's got a lot going on, or a branch that lasts more than a few minutes in a non-trivial team, then what's going to happen is you're going to have some conflicts. Even if they're not really conflicted, files will have changed in both sides. We need to make sure that they're not going to cause any problems. There are a number of merge strategies that Git uses. This is, I'm going to skip over this quite quickly. Unfortunately, it is basically a talk to itself. Suffice to say, Git uses multiple merge strategies. They're pluggable, which is nice. So if you have some proprietary binary format that you obviously can't merge binary formats if you don't know what they are. But if you personally know that your binary format is really just a lot like a binary XML, and you could possibly merge two changes if they're non-conflicting, then you can write your own merge strategy for that. But the one that Git uses by default is something called recursive. Recursive is interesting. It's been extensively tested on a Linux kernel tree, which is probably about as busy a tree as you're going to get. And it's very clever. What it does is it walks back through the tree, and at each branching point, it creates a dummy intermediate commit, and then recursively works its way up the set of changes. As I say, this is a fairly big subject in itself. If you're interested, have a look at it. There are other types of merge that can occur. There's something called hours, where you can essentially just completely forget the history of a master branch and replace it with a entirely different branch while keeping the context. Not often used, but is kind of handy sometimes. As I say, I'd like to talk more about this, but it is a massive subject in and of itself. I recommend going and having a look around and some of the discussions of how it works internally. But suffice to say, the recursive merge system has been extensively tested on the Linux kernel. So we're going to come to one of our old friends. How many people here have used Rebase at some point? Right. How many people screwed it up? Yeah, about half. Yeah, again, rite of passage. So now we know a little bit about the object graph of Git, how it all wires together. Hopefully, Rebase becomes a little bit more obvious what's going on. What Rebase does is it takes the branching point that occurred, where we decided to move on a separate track, and it just says, I'm going to overwrite that, I'm going to change that. But because it's all hashed, we need to replay each commit on top of the new point where we're going to sort of rebind the history. This is extremely powerful, because if you want a clean tree, this is how you do it. Because from this point on, you can now do a fast-forward merge if you want to have a completely flat history. It also is exceedingly powerful because at each one of those replays, you have the ability to go, hang on, I don't like that commit message, I'm going to change that. Or I would like to take these two commits and put them into one. Because we're replaying, we get to interject and change history, pretend we did something else. We're going to cheat. But that is also quite powerful in itself for reasons I'll show you. Rebase is one of those things. It's pretty easy to screw up, but you will also find it's very, very useful. One of the most powerful things is the idea of an interactive rebase. So you say, I'm going to rebase, I'm going to replay this. Before you do that, show me what you're going to do. And then you can go in and say, well, actually, these two commits should be one commit, or these two commits should be one commit and have this message, or this message should be edited, or I was going to squash the whole thing down into one big commit, which is an option. Don't recommend it. I personally like to keep history, but some people like a clean tree, as I say. There's lots more I could talk about here, but this is really the core of Git's model. You've got your objects, you've got your refs, which you can build branches and tags and anything else you want on top of that. And then you have, slightly higher than that, you have the idea of a merge, where you're going to have to resolve changes between different branches at some point. And you want to keep the history, so you can, Git has metadata in the commits that allow you to store where an object came from, where a piece of history came from, how you got there, which is why merging works so much better than, say, Subversion. Subversion does not have its own history in its repository. Git does. Git knows where it came from, therefore it knows how to get out of trouble. Talking of getting out of trouble, did you see this ad here? Did this appear in the UK? The original Prince of Persia or the new one, the Sands of Time. It was an ad. I think it was only in Australia. No? Okay. Anyway, you want to get out of trouble. Everyone has screwed up their Git repository. Generally speaking, as I say, it's a rite of passage for new Git people to go like, oh yeah, I know what's going on here. I'm going to reset, or I'm going to rebase, and oh shit. So here's our favorite one: reset hard. Everybody's done it. I know about half people said, no, I didn't screw this up. You were probably lying. We've all done it. So it reset hard. Destroys pretty much everything. It moves the ref back to some point, maybe somewhere completely else, because you can essentially hyperspace right through the tree to somewhere else. And it will also blow away any stage changes. It will blow away your working tree. It's very useful. I use reset hard a lot when I've gone like hack. Oh, I've got myself into a mess. Reset hard, and it just puts me straight back to, the head in a clean state. But you be aware when you do it, you will be blowing away a lot of potential data. Now, I can't help you with the actual working changes. I can't help you with anything's in the working tree but hasn't been added to Git. Can't help you with that. But anything that Git's aware of, we can get back to. So, anyone want to take a guess at how we would get out of this situation, knowing what we know now? Yeah, you can use these newfangled IDEs. I don't know, you kids. Well, we talked about the Riff Log. So when we did that reset, there would have been a record of that. So we can find out where we were beforehand. So we go to the Riff Log, find out where this particular ref was pointing previously, and go, well, okay, now we know we want to go back to our commit, not moving of it. By the way, these are little up arrows. There's a whole little mini language in Git about how to reference refs. So you can say like ref -1, then ref -2, or jump 2 places back in the tree, whatever. It's fairly complex. I don't really use it very much myself. It's just too much to remember most of the time. It's easy to just look through the logs and find out where you want to get to. But that head uptick means the previous commit to the one I'm currently looking at. So we know the hash now, so we can find it up here. And we go, okay, fair enough. Let's just use the same thing that got us into trouble to get us out. Git reset hard, pushes it straight back onto where it was. Now you're out of trouble again. Hopefully. The other great one, I'm pretty sure everyone who's rebased has probably seen this, or at least a non-trivial rebase. You've done a rebase, and you've broken the build, and you don't quite know why. Somewhere along in that tree, there was some sort of conflicting error. Not conflicting enough to cause a merge failure, but conflicting enough to be a logical failure. Much, much worse than a merge failure. Merge failures are easy. Logical ones can waste weeks of your life. So what do we do about this? Now, this actually can apply to a couple of things, including merges themselves. But rebase is a particularly good one. I like this one because at one point I had a long-running branch, and I was constantly rebasing, and every time it would break in some way, shape, or form, and I had to go and find out. So how can we do this? Now, I haven't quite covered this in detail, but I did mention that when you do a rebase and you replay, you actually have the ability to interject at each point and change the history. Or you could interject at that point, not change history, but, for instance, validate what's just happened in some way, shape, or form, like those complete 100% test coverages that you all have naturally. I've certainly got 100% test coverage. I assume I've tested it all. So we have the ability to undo things. So let's undo that. The first thing we're going to do, reset. We use Riff Log to reset this. Now, we can actually use something called RebaseExec. RebaseExec, at each step along the rebase, will run a command for you. In our case, our totally awesome 100% complete test suite can be run at each point of the rebase, and it will fail the first time the test failed. So you can find out very quickly why your rebase failed, and you can either decide to fix up at that point. Git will literally just stop at that point and go, Do you want to fix up? Do you want to abort this rebase? It gives you a bunch of options. You have the ability to go, I'm going to decide how to fix this up. So you can see we stopped halfway through the rebase here because our test failed because we did make test. Now make test can be anything. It can be MVN test. It could be MVN int test, which is our particularly extreme tests, which literally run up Postgres and a full Tomcat server and the whole works and throws tons of tests at it. Depends on how bad your situation is. But you have this option. You do the rebase, and you get to say, check each step along the way. Very, very useful tool that if you do get into this situation. Particularly if your tests are fast, do this every time. It saves you a lot of trouble down the line. However, it's not always possible to go back and change history. Sometimes you want to fix in place. How many people here know about Git bisect? Okay, handful. Now, one of the classic ways you would fix this problem, because in Git you can jump around in history, the moment you realize that, you go, oh, what I can do is go back through the tree and run the test each time and work out which one was wrong, and then I can fix it up afterwards. It helps me narrow down at what point, which commit broke. And this doesn't just apply to rebases, it can apply to merges, it can apply to just a completely flat tree where you're making changes, and you realize later on, weeks later, that you had broken something somewhere, but you don't quite know where. They use it a lot in the Git, in the Linux tree. But what it does, it basically goes, I tell Git, okay, so we're going to start a bisect here. We're going to pick this point that I happen to know that's broken. I'm going to pick this point, which I happen to know was working. Run back through that history, running this command. You can either do it manually, you can jump through and do a bunch of manual testing, and then say that was marked as good or bad. Or you can just get it to run a command, and it'll run those tests. It'll jump back. But what it does it the smart way. It does the way you do if you thought, this is going to take ages, how can I make this faster? It'll pick a point somewhere in between the good and the bad, do a test. If it's bad, it'll go further back in time. If it's good, it'll jump forward in time. And it will automate this process of finding out what exactly happened. Now, I just realized, I think I'm running severely over time. Is that true? I think I've been talking for almost an hour now, so nobody's come and shouted at me. Okay, cool. But anyway, I'm at the end. As you can tell, there's a lot more I could be doing here. There's lots and lots of examples you can give, but hopefully I don't need to. With this basic knowledge, you got your objects and your commits and your trees. You got your refs that you can move around and you can manipulate directly. If you're really excited, you can jump lower down. And you can chain these commits together, and you can have multiple parents, and you can re-merge points in history, split at history. But really, it's just all just objects that are pointed to by trees, that are pointed to by commits, which are pointed to by references. And once you know that, so many things kind of fall out. Once you understand that model, everything else that's built on top of that, all these complex ideas, are really just layers on top of that, and you can work from first principles. And if you have a question, you can go work through it. What happened? Well, if I was writing reset, if I was writing rebase, how would I implement it? Oh, right, well, in that case, I can probably do this. A lot of things become obvious. So now we have all this extra knowledge now. Hopefully you can work through from first principles for any issues you have in Git, and hopefully you understand and use Git in a different way. On the other hand, if you're feeling really excited, there's lots of low-level commands to manipulate Git trees directly. So why don't you just go back to your production trees and just start hacking on your refs, and maybe look at cat file and hash objects and all these fun ways that you can directly manipulate a tree. If anyone's interested, like, there's a really fun story about how the Linux kernel completely blew up Bitbucket one time because of some dark magic that people did with public keys. But Feel free to go off and learn more about Git and understand it more, and use it in a more powerful way. It's just an acyclic graph, but it's also just a bunch of objects, and you can manipulate them. And any programmer can mess with this to make the workflow more powerful. Or if you're really excited, go off and implement Git. You could actually implement the core of Git in an afternoon. Now, you can't do a lot of the advanced stuff. You can't do the pack files. You can't necessarily do network. But you could basically write a program that will actually walk across the Git tree and tell you what's in it and report things. Very, very simple, very powerful if you know how it works. So hopefully this has been useful to you. Rate this on the app if you would. And hopefully this will help you with your further Git hacking.
Fantastic. Question. So Git seems to me like it's good for sort of small-scale, single software problems. What if you've got a very, very highly modular system of, say, 900 modules, and you want to manage, obviously, the release of every single module independently? I don't want to have a master branch that says, this is my current state of 900 things. I want to branch everything independently. How do I do that?
There's a couple of options. I mean, first off, the Git is not, it's definitely capable of handling massive projects. I mean, it was built for and used by the Git, the Linux kernel, which is one of the biggest, most active software projects in history. So it's more capable of doing that. Now, you talk about modular systems. That's really a software engineering problem, not a version control system. We had a system, our system for a while was very, very modular. What you find there is you have to have good API separation. Ultimately, either your two modules are independent and they talk via a stable API, in which case they can be released separately, or
either they're released separately and they talk via a well-defined API and it can be released separately and can operate independently, or they have implicit or explicit dependencies on each other on their versions, in which case they are not really separate pieces of software. If I'm using Amazon Web Services, I do not require that Amazon to upgrade their services at the same time that I upgrade my system that talks to it. However, if I do, then I really am part of Amazon Web Services. We've been through this, and it's often one of those cycles of software where you separate things out, and then you find they have implicit dependencies, and you rejoin them. We ended up rejoining a bunch of our stuff when we found out that their APIs were not really as independent as we thought they were. Or in some cases, we had a bunch of modules, but we really wanted to refactor them into a different structure of modules, in which case we would rejoin them all to get all into the same repository, treat them as a single piece of software on a single version for each release, and then only when they're fully API separated would you then split them up again. That said, splitting up something when you put it into the same repository is exceedingly hard, because once the possibility of creating tight coupling occurs, it will occur. It's just human nature. If I know that piece of software over there has a contact or customer object, I'm going to end up using that customer object rather than writing my own and having a bunch of data transfer objects. I'm going to take shortcuts. It's the reality. So either you have very strong, very separate APIs, or you have the acknowledge that they're all part of the same project and may need to be upgraded in lockstep. It's not straightforward. One of the things that Amazon did in particular, one of the reasons why Amazon Web Services exists was because famously it came down from the top. Everything will expose itself via REST API. There will be no cross dependencies between our different tools, our storage system versus our computing system. And they enforced that very hard, and from that they were able to turn it into a product because they were forced to operate as customers for each other. Anywhere where you've got two people who can collude together, you're going to get this kind of bleeding of dependencies. So they had to have strong separation. There was a funny quote by Peter Seibel on Twitter the other day. He's a guy who did Practical Common Lisp. Even if you're not into Common Lisp, read the book. It's one of the best technical introductions to a language I've ever read. But he said, this is Conway's law for the 21st century, for the cloud century. Any geographically distributed team will be talking to their software will talk via an RPC interface. So my corollary to that was, if you want to create RPC interfaces, physically separate your team. If you want microservices, make everyone work from home. So that's a long answer. Git is more than capable of dealing with massive structured projects. It's used on probably the largest software project in the world right now. Whether to split or merge different modules depends entirely on how strong you're prepared to commit to a stable API over time, and how much you can stop people from assuming that they know what's going on under the hood of different modules. Even if you've got strong APIs, if you implicitly depending on a certain behavior, then if you change that behavior, it will break, even if the API remains the same. Microsoft Windows is a famous example of this. They had to keep all the old bugs and quirks over time, because any fixing of a bug would break something for somebody for whom that was not a bug, it was a feature. So that's pretty much. So that's the long, rambling answer to the question. I hope that helps.
Any other quick questions?
Rebase versus merge. Usage scenarios, would you use Rebase versus merge?
Rebase.
The question is, when would you use Rebase versus merge?
Sorry, yes. Yeah. So, okay, so Rebase versus merge. Generally speaking, merge. Unless you have some pressing reason. Now, some places they will prefer a clean tree. Rebase will give you a clean tree. Rebase is also the ability to fix up a branch. It gives you the ability to go, look, I've created a whole ton of commits. I've got commit A, oh, fix the commit A, fix the last commit. Oh, oops, I forgot this file, blah, blah. And each one of those intermediate commits is broken. And ideally what you'd like is to have each commit be a complete self-contained change, atomic but discrete. So Rebase gives you the ability to do that. As part of your rebasing, you can modify that history. Now, one thing interesting about Rebase is you don't actually have to give it a different hash. You can actually say, I want to rebase onto the place I'm already pointing from. But in doing so, please let me interject and change the history. So this is one of those weird tricks. Rebase can rebase onto anything, including onto itself. So you can actually go rebase. What rebase should be really replay. Will be a better name for it. So replay this history. I want the history to start somewhere else, or I want the history to carry on starting here, but I want to actually modify that history at each point. So generally speaking, we prefer merge, no fast forward, rebase when you need to change history, or you've diverged so far that really the only way to do it is to rebase. That doesn't really happen very often, and generally speaking, you're going to have breakage at that point. I've done that. But you can also merge history back into your tree, but that will often end up with quite a messy tree. If you want to keep your tree fairly clean, rebase, but don't overdo it. And also, you've got to bear in mind, if you're rebasing a branch and then you push it up, you're going to destroy the branch for anyone else who's using it. Because you're rewriting history. When they pull it down, it's going to kind of change their history. That's why you have this idea of force pushes. If you push something and it's completely changed the history, the server will refuse it unless you say force. That's because your hashes, the head has changed completely. It's now a completely different set of history. If someone else was using that history and they go and pull, the whole thing becomes chaos very, very quickly indeed. There is something called force with lease, by the way. I wrote an article about this a few months ago, if you're interested. Force with lease, when you push and you do a force, you can do a force with lease. And what that does is checks if anyone else has been using that branch as well, and then it'll refuse to do the force, even if you said force with lease, it will then no longer overwrite it because someone else has worked on that branch as well. It's not perfect, but it does help. But no, the short answer is, by preference, merge with no fast forward, rebases for cleaning up only, unless you really, really are working very much independently and really want to fix things up. The moment you're sharing a branch, you should never rebase. That's a golden rule on a Linux kernel, for instance. The moment you've done a rebase or pushed any branch up somewhere, rebases cannot occur. Rebases are a local only operation. You can treat them as an operation to push up to a tree, but if you do so, you're potentially stomping on someone else's work. So again, that's a slightly long version of it.
Fantastic. Thanks very much, Steve.
Thank you.